All right, our goal for this video is to talk about using energy in a mass spring problem or mass spring system. So there's different types of energy, both kinetic and potential, and I think this would actually help to start with a screen share. Let me get it ready. I'm going to stop this. All right, and share this one. Whoops. I want to use this window. Okay, so hopefully you're looking at this right now with me. Move this up here. So what do we have? We have a mass hanging on a spring. Now, one of the things that's annoying about this simulation is in the last part of the simulation, it showed the center of mass being the reference point of zero. I want to show you something here. In particular, notice what it says height equals zero is, and watch this, watch the potential energy due to gravity. So let's watch what happens to that. And you could watch the potential energy due to the spring as well. Right now, there's a little bit of both because we're at non-zero height. Watch what happens as I lower this thing down. Notice when the bottom of the mass is at height equals zero, it says there's no potential energy, even though the center of mass is not at zero height. So in this part of the simulation, for whatever reason, we're going to use the bottom of the mass. So let me go ahead and do some work on this. Let me stop this thing. Let's put a, let's see where it says. So no, it's driving me, whatever. That's fine. That's part of life. Hey, they do a great job with these simulations. I'm going to reference this as Y equilibrium, and we're going to use the bottom of the mass for everything in this problem, okay? All right, so let me get rid of that, and let me erase this crap over here. All right. So now what I want to do is I'm going to pause this simulation. I'm going to pull this thing down and I'm going to release it. So in this case, maybe to see the whole graph, let me zoom out a little bit. I want you to pay attention to the different types of energy, oops, that appear over here. In particular, here's the total amount of energy. Right now, there's zero gravitational. It's not moving yet, so there's no kinetic. And then here we see it's all potential energy associated with the spring. So spring potential energy. They're calling it elastic potential energy. That's fine. Also notice what I've done here is I've turned off the damping. So there's basically no friction, no air resistance. This will go on forever. And I'm going to now run this thing and I'm going to run it in slow-mo. Watch what happens to those different types of energy as this thing moves up and down. Right, here we go. Okay, we could see it oscillating between various forms. Right. Now here's something interesting. Look at the very top of the oscillation. You see how the spring is compressed a little bit? When it's compressed, there's still some spring energy at the very top. I can show you this here. So if I put this movable line here, right, and actually I'll pause the video, right? So right at this point, we're referencing the bottom of the spring. Oh, whatever. I'll put this right here. So this movable line is indicating where there is no displacement, right? You can see it's basically zero. Let's get it to zero. Okay, so the red line there, now if I run this thing, it doesn't go all the way to the bottom, so there's still some gravitational energy at the bottom. So again, I'm looking at these energy levels over here as it's moving up and down. The point being, we see that at various points in the oscillation, you can have spring energy, potential energy associated with the spring, potential energy associated with gravity, and kinetic energy. And it could be something crazy where even at the top, there was some little bit of spring energy. Again, just showing you this case where we set this, if we have zero gravitational here at the bottom, we see the spring is compressed a little bit at the top, and that's why there's some spring energy at the top. Let's get to the equations on the board so you can actually solve some problems. So let's stop this share. Whoops. Stop the share. Okay, there we go. So you probably know this already. We saw the kinetic energy moving up and down. What's the equation for that? 1/2 mv squared, which from our previous video, maybe you recall, that was minus omega naught x max sine of omega naught t plus phi. Squared. In this case, the minus sign will drop because it's inside the parentheses. All right? If we square that equation out, maybe you're faster than me, I get a 1/2 m omega naught squared x max squared. Remember, x max, amplitude, same thing, but we get a sine squared of omega naught t plus phi. The spring energy. What's the equation for the energy associated with the spring from physics 1? You better know this. It's 1/2 kx squared. But remember, x is some function of time, so that's going to be 1/2 k. K is the spring constant in this case. X was x max cosine of omega naught t plus phi. And that's all squared. Kind of running out of room here, so that's 1/2 k x max squared. That's still on screen? Just barely. Okay, that's a little sloppy. Just barely. Okay. So now, gravitational. We're going to ignore this if the system is horizontal. But when the system's moving up and down, we better account for it. So that's going to be mgy. This equation is tricky. So what is y? Let me give you an example here. It's going to depend a lot on how you choose your coordinate system. Now, in our first example, we set y equal to 0 at the top, and then we said downwards was the positive direction. We said that this level was y equilibrium, and then this would be y equals 2 times the amplitude down here. I guess 2 times y max. So you could try and figure out an equation based off this. One of the things when we're doing these equations, we usually say y as a function of time is equal to y max times times cosine of omega naught t plus phi. You could do this, right? And then where this gets sneaky here is now the if you're going to use this coordinate system, y is upside down, you're probably going to have to stick a minus sign on here. And perhaps an easier method might be to set y equals 0 at the bottom of the oscillation. We still call this y equals y equilibrium, and we'll call this y equals 2a. So now going the very bottom of the oscillation is y equals 0, and then we could use mgy. Now, you might be saying, can't I just plug in y equals this? We got to be a little bit careful here. Notice that this equation right here is relative to y equilibrium. So if you want to use it over here, this still won't work. We should use mg y equilibrium plus y of t, where y of t is this goofy equation. Now, you might be saying, well, I like when we started this at the top. You can always fix that by using a phase angle of 180 degrees or 90. So this is now a slightly better way to do it, maybe less confusing. We set y equal to 0 at the bottom of the oscillation. We say that it's twice the amplitude at the top, y equals 2a at the top. The equation y of t is relative to this equilibrium. So if you need the y coordinate for doing potential energy, you say it's y equilibrium plus y of t, and then we ignore all this crap over here, right? We say y is equal to 0 at the bottom, and we use up is the positive direction. All right, so hopefully that helps you. I'm going to make another video right after this where I try to summarize the trickiest points. I'll probably remind you of this in there. But maybe let's look at this in the Excel spreadsheet just so you can see how this works out. All right, let's go to Excel and let's share. Come on. All right. So if you wanted to get the kinetic energy, just for example, I guess I should italicize that variable, Control I, right? I could say this is equal to 1/2 or 0.5 times the spring constant, whatever that is. K, I don't have a K. Let's give it a K here. Ugh. All right, I didn't think this through. I don't have a spring constant for this one. Whatever. I guess I could just make one up, right? Italicize that. Let's just say it's 10.0. Right? So this is equal to, and I guess maybe what I'll do is I'll call this K. So equals 0.5, that's 1/2, times K times, I could literally just click on this and square it. Oh, crap, the units. You know what I'm going to do? I'm going to be like this. I'm going to insert a column. I better watch out for the right units. Equals this divided by 100, right? And I can fill that down. And so now, right, I can't use centimeters and newtons per meter to get joules. I got to use meters. All right. So now this is equal to 0.5 star K times X, right? Now in this case, I could also use 0.5 star the amplitude, which was A. I'd have to divide it by 100 to convert the units from centimeters to meters, times X, let's see, times what was it? Cosine of omega times time plus the phase angle in radians. Here we go. And then I want to square that. So I could do it that way as well. Right? And if I plot this thing, it's probably worth plotting one of these. Insert charts. No, okay. So what we could see here is a couple of things. This was, what was this? Spring potential energy versus time. All right. I'm not going to mess around. One thing is we see it looks kind of goofy. Do you see the shape doesn't look right? That's entirely due to the step size. Okay, so I'll show you, I'll fix that in a minute. So these goofy shapes right here, it should be a nice smooth curve. That's because my step size is not small enough. This thing is oscillating twice as rapidly. So notice this does, let's see, it's completing two cycles in, how about this? It's completing one cycle in 0.2 seconds, where in 0.2 seconds, look at this one, it's completing 2 cycles. So the energy oscillates twice as fast. Cosine squared goes to something like, what is it? 1 plus cosine, I'll just say it like this, the double angle formula, cosine of theta squared. We can see that if you have a frequency, it'll get doubled. That's what's happening here. So that's one thing. And then furthermore, let me clear out those annotations. Let's show that this smooths out a little bit if I use a smaller step size. So now we could see it definitely is a nice smooth function. It was literally just the step size. Let me do this so we can see if it's smooth here at this level. So hopefully you can see that a little bit better. So it is a nice smooth function. Another thing to notice, this one goes plus negative. Do you see the axis right here? Right? And this one, the axis is at the bottom. So this one's only positive. The spring energy had that squared in it, which makes this positive. Now, perhaps one last thing I want to show you here. I'm not going to do the, what? That was not kinetic energy. That was spring potential energy. I'm an idiot. Whatever. I just want to show you that you could also get spring potential energy. I'm going to stop formatting, but it's equal to 0.5 star K times this X value, and then we square it. And that looks a little bit prettier. So in a spreadsheet, it's nice and easy. All right, so and I'm sure you could make a comparable graph, and I think I asked you to do this in the homework, so that's something you can do, but you can make the kinetic energy. Maybe I'll show one more thing. Since this is here, I did want to run this again. Notice that the total energy is constant, right? The total energy is constant. So when you get sine squared from the potential energy, sine squared from the kinetic energy plus cosine squared, you'll get 1. Let me show you what I mean on the big board. You add these two terms together. It may not seem obvious right away, but those two terms do add up, and it's hidden right here. Omega naught squared is the square root of K over M squared, which equals K over M. So notice this term right here ends up becoming, the M's drop out, you get 1/2 K X squared sine squared. This one's 1/2 K X squared cosine squared. When you take these two terms and add them together, they add up to 1 because sine squared plus cosine squared is 1. Be careful, they add up to 1/2 K X max squared times 1. So the energy associated with these two together, the kinetic energy and the spring potential energy, is this constant value. And then you have some, possibly some gravitational energy that gets in there as well. All right. But we know energy is conserved. A vertical mass spring system gets a little bit trickier. We've got to account for this Y equilibrium position. I think that's enough for right now.